Swayam Prabha. Digital India. Educated India.
Right. So this is the problem. Minimize f of x, g of x is 0, and we want to see what does it mean to say there must not be a descent direction that is also feasible. That's what we'll try to find out now, right? So let's say this was x star. Somebody gives you this x star and claims this is the solution, and then your gradient was pointing in this particular direction, right? So now question is, so what are these directions? So any direction here is what? Why? So feasibility means what? So feasibility means your constraint is getting satisfied. But then this is all I have said is about the gradient of the objective, right? So if I am at this point, what are these directions? What will happen to the function f if I move in this direction? These are all descent directions, right? So these are all our descent directions. We just saw this, right? Reason being, so any direction, any point here d, right, this or this or this or this, whichever point you take, let's call this d. So your d transpose del f of x star will be less than 0, and hence these are all descent directions, right? So okay, so now we want to relate this to feasibility, right? Because that's what we want. So we do not want a descent direction that's also feasible. So let's say at this point x star that somebody gave you and claims as a solution, your gradient to g was pointing in this direction, right? So now we want to see if x star is the answer to the question that we are asking, if x star is an optimal answer or not, right? So which means we want to check the condition at x star, is there a descent direction which is also feasible? That's what we want to ask. So what is our constraint? Our constraint is g of x equals 0, right? So we know that if I move with this is the gradient of g, which means all these directions, your g will actually decrease. These are descent for g, right? In all these directions, your g will increase. So in these directions, your g will stay the same, right? So the green line, this line, are the directions in which your g does not change. Now tell me the answer to this question. In this picture, is there a descent direction that is also feasible? So is x star optimal or not? So how will you find it? So these are feasible directions. This line is the set of all feasible directions. And these are all, let me go back. These are all descent directions, right? So now I'm asking, is there a descent direction which is also feasible? Which means I want to see if the intersection of these two sets is empty or not empty. And is it empty or not empty? Not empty, which means what? So because I can always move in this direction, let's say I move to this point. So why is this point? So this is like x star 2, let's say. Why is x star 2 better than x star? Why should x star 2 better than x star? Because this is a descent direction, which means if I have moved in this direction, my function value will reduce, f will reduce, and my goal is to reduce f as much as possible. So my function is reducing. At the same time, I am also satisfying my g, right? So the constraint is also satisfied, and I'm also reducing my function. So which means this is a better point, right? So if I had to bet on x star, I would rather pick x star 2 than x star, because the objective is also smaller and the constraint is also satisfied, right? So which means this cannot be an optimal solution because there is a descent direction which is also feasible. So this can no longer be an optimal solution, right? So now, okay, let me. Right. So now, what about this? So if your x and del g of x are pointing in the same direction. So is there a descent direction which is also feasible? So let's call this as x star. So what? So let's say if I move from here to here, this is x2 star. So what is the problem with this point? The constraint is not satisfied. Though I have reduced my function, but I have missed out on the constraint. The feasibility is gone, right? So the feasibility is only on the green line. So there is a descent direction, but it's not feasible, right? So, so these are all feasible directions, but these are not descent directions, right? So because my f is not reducing in this direction, which means in this point x star, there is no descent direction which is also feasible. Correct? Is that clear? So which means this point satisfies all the necessary condition for an optimal solution. Any questions on this? So can you think of any other direction, any other way in which del of f and del of g can be related such that there will not be a descent direction that's also feasible? There is one other way in which it can happen. What could that be? We know this is not the answer. We know this is an answer. This is potentially an answer. In what other way can del, the gradient of f and g be related such that there is no descent direction which is also feasible? Sorry? Opposite to each other, right? So anti-parallel vectors. So if this is the direction, what happens now? So again, the feasible set is exactly this, right? The ones that is perpendicular to this, and your descent direction stays the same. You still don't have a descent direction that is also feasible, correct? So it can either be parallel or anti-parallel, and still things are okay, right? So how can we, now we need to kind of succinctly put together the relation between del f of x and del g of x. So what is the relation between del f of x and del g of x, right? So for which this condition can hold. If I had to write del f of x star and del g of x star, how should these two be related? So if we have to relate this as an equation, what is the relation? Sorry? Mod del g, why is there a mod? Okay, so he is saying, so del g or minus del g, both are okay. That's what you're saying, right? And hence you're saying this should be something like this, right? So here's the question. So in this particular example, so this was del g, this was del f. So do the lengths of del g and del f matter? Only the direction matters. The lengths don't matter at all, right? So which means in this case you are making an explicit constraint that these two are of the same length, right? But that need not be the case, right? So which means I can just say this has to be some lambda times del g of x star, or otherwise, or some minus lambda times del g of x star, doesn't matter. And there is is there any condition on the lambda? So it can either be positive or negative, because it can be either in this direction or in the opposite direction, right? So what we'll say now is the condition that captures the fact that there is no descent direction that is also feasible in the case of a constraint optimization problem such that there is a equality constraint is this. Del f of x star is minus lambda times del g of x star. So that is what we have kind of come to conclude. So let's go and look at a slightly complicated problem. Not really complicated problem, a different case that we also have to consider, because this is the case that we started off with, right? So we wanted to minimize a function f of x such that g of x is less than or equal to 0. So on our cow rope fence example, you had those two constraints. One was the rope constraint, in which the cow can move anywhere within the rope, which means the distance, I mean, your x minus 2 squared plus y minus 2 squared was less than or equal to 1, which can be written as a function of this form, g of x less than or equal to 0 also, right? So now let's look at this case and see how the same question about there not being a descent direction, which is also feasible, works out in this case. So let's take the same example and see what, so you can tell me what happens. So let's say this was my del f of x star. So where are the descent directions? Same question as before. So which are the descent directions? So these are the descent directions, right? This is what we saw earlier. So let me actually do it in this way only. We do the same thing. So these are our descent directions as before. So now the only difference between previous case and this case is, in the previous case we had g of x equals 0. In this case we are saying g of x is less than or equal to 0. And we want to see how that really affects the case, our case, right? So now again, so ask the same question. Let's say at this point the gradient at g was pointing in this direction, right? So now what happens? So is there a descent direction which is also feasible? Why is that? And which direction is that? Perfect. So intersection of red and all the points below the green. In the previous case it was just the green. In this case it is all the points below the green. And why is that? Why? What has changed? Less than or equal to 0. So if this point had less than or equal to 0, let's say this was feasible, and now if you reduce, it can only stay less than or equal to 0. G can only stay less than or equal to 0. And because these two half spaces kind of intersect, now there are not just on this line, so any direction here, 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 all these directions are descent directions which are also feasible. So hence this cannot be an optimal point, right? So now let's see this point, right? So what happens in this case? So is there a descent direction which is also feasible? Which one is that? The whole red region, right? Because you can always move anything in the red region is also a descent direction for the green, right? So this was a case in the previous case which was okay, but here this cannot happen, right? So this is also not possible, right? So this is also wrong. This is also wrong, right? So now what is there an answer at all to this? And if so, what would be the answer? So how should f and gradients at f and g be such that you can claim that there is no descent direction which is also feasible? Sorry? So she says the dot product should be 0. Let's just examine that a moment. If the dot products are 0, so let's say if this was your x star, oops, right? So all these are my descent directions. Let's say the dot product was 0, which means it is somewhere here, right? So your g is somewhere here, g of x star. So for g, the descent directions will be this, right? So which means I have areas here where I can move, where there is a descent direction which is also feasible. So the dot product being 0 is probably not the answer to this. Opposite directions, yes. So the opposite direction, so what happens? So if this is the direction, so del f and del g are opposite to each other, what happens now? Now these are all my descent directions for f. These are all my descent directions for g, right? Right? So which means if I move in this descent direction for f, I am actually increasing g, and that's a bad thing, right? So there may not be a descent direction which is also feasible, correct? So which means this is the case for which this is a necessary condition for optimality, where you have the condition that g of x is less than or equal to 0, which was not the case earlier, correct? So how can you now formalize this? So this was the previous case where we said del of x star is minus lambda del g of x star. Now, what additional conditions has to be put on this for the case of g of x less than or equal to 0? What can you say about lambda in particular? Lambda has to be positive, because if lambda is negative, what happens? F and g becomes the same direction, and then that's a problem, right? So the only difference between the previous case and this case is your lambda in the previous case was unconstrained. Because you are making a constraint on the because now it becomes an inequality constraint, it directly translates to the fact that lambda becomes a that's a constraint on lambda. So now interesting way to solve this problem then is as follows. So this is what we said. So for the constraint optimization problem, your del of f star is minus lambda del of g of x star. Now you convert your constraint optimization problem into a unconstrained optimization problem, right? So what you do is you add your g of x, which is the constraint that you're trying to satisfy, with a particular multiplier lambda to your objective function itself, and try to solve this in an unconstrained fashion. Right. So now, because now for the, if you try to set the derivative of this to 0, right? So now you have del of f of x star, right, plus lambda del of g of x star is 0, right? And that is exactly what we said is the necessary condition for a point to have descent direction which is not feasible, no descent direction which is feasible rather. Right. So on this way of solving this was introduced first by Lagrange, and this lambda is famously called as the Lagrange multiplier, and this will also play a role as a regularizer in all ML problems, which we'll also see in the next talk bit, and also in the later talks today by Shaheli. So we have not done a lot of things in optimization. We have just said unconstrained, you can solve using gradient descent. If it is a constraint optimization problem, you can convert it into an unconstrained optimization problem, and by using the Lagrange multiplier formulation. So there is much more to it. So for example, what happens if there are multiple constraints? How do the descent and the directions change, and so on? So we'll try to cover a bit in the tutorial session if possible. But this should hopefully give you a flavor for what this is about. So let's come to the, so this was a detour to some constraint and unconstrained optimization problems. But then the problem that we tried to solve initially was still an unconstrained optimization problem. There is nothing constraining the W's that we actually had. So we just wanted to minimize W, f of W, where f of W was this, right? So now how do we solve this problem? Now that I have spoken so much, how will you solve this problem? So this is an unconstrained optimization problem, and the way to solve this is just gradient descent. So all you need to know is just the gradient at any given W for this function, and this can be computed like this. Note that there is no inverse involved in this computation, which was the original problem that we started off with, right? If you had to solve this in an exact fashion, the W had an inverse, and we wanted to get away with that. So this gradient computation does not have any inverse. It just computes this matrix, and this matrix can be computed only once, right? So this just depends on the our function, our input x's, right? So somebody gives you m different data points, you can always compute xi transpose and sum it up over all m's. This again comes from our data. So these two, this matrix A and this vector B, can be computed, pre-computed, and you have it. So for any W, given W, the gradient is just W transpose A minus P, which is easy to compute, right? So all we do now is you start with t equals 0, right? Initialize maybe at random to some vector in RD. You have some vector in RD to which you want to initialize W, WT, and then WT plus 1, the next W that you care about, is Wt, which is the current W, minus some step size times the gradient at Wt of f, right? So, and this is easy to compute as we saw, right? So now you can do this computation and then repeat. So this will be our iterative linear regression algorithm. So this is this that we want to solve, right? So this is as simple as that. So when will this also be problematic, right? So the only step, it's a single line code, right? The only step you're doing is you're starting with some W and then taking a step in the direction of the gradient. So the only problematic step, if at all any, has to be here. And what problem might potentially happen in computing the gradient? The only problem is when you have a huge number of samples, computing this might be computationally tough and so on. So one way to solve that is instead of computing the gradient, I mean at all the points, computing the sum over all the points, you only look at the gradient with respect to a particular set of points. You assume that the data set is smaller at every point, and then you do you only do gradient with respect to that smaller set of points. Let me. So that would be what is called as the stochastic gradient descent. So it is the same algorithm, the gradient descent. So we will do more of this in the tutorial session, I think on 13th. So the idea here is that, so you don't have to even compute your gradient with respect to all the data points. You only compute it for a smaller set of data points in a batch, or even in the extreme case, you just compute gradient with respect to one randomly picked data point and move in the direction of that point dictates, and pick a different point at every iteration and keep doing this, right? So this we'll talk slightly more detail in the tutorial session, and this is called as the stochastic gradient descent algorithm. So this is all I had to say today. I think I probably, yeah. So this is all I had to explain today. So to summarize, what we saw was we started with the problem of iterative linear regression, where you wanted to have a iterative algorithm to find the best W. The problem was computing these inverses, and that's why we wanted this iterative algorithm. We looked at unconstrained optimization problem. We saw gradient descent as a good method to do that, which picks the negative of the gradient as the direction to move. We saw problems that might occur if you don't choose step size carefully. We also looked at the constraint version of it. We only looked at two special cases with a single equality constraint and a single inequality constraint. And we saw that in both the cases, there is a natural way to relate the gradients of the objective function and gradient of the constraint, and using what is called as a Lagrange multiplier. In the case of inequality, there is a condition on the constraint on the Lagrange multiplier that it has to be positive. And you can convert your unconstrained problem, a constraint problem, into an unconstrained problem and then solve it using the Lagrange multiplier trick. And in the case of linear regression, we don't even need that. Right now, we don't have any constraint on W. In some cases, you may want to, as we will see later on, right? So you may want to have conditions on W such that your norm of W is less than or equal to some constant, right? So you don't want your weight vectors to grow like too much, right? So this is something that we will see in the next session. In those cases, you want to solve this with respect to this constraint. Now it becomes a constraint optimization problem, where you need to convert this into a Lagrange multiplier formulation, which will also lead to what we'll see as regularization and how it links to model complexity and so on in the next class. So I think I'll stop here. If you have any questions, we can probably take it. So the step, yeah. So one thing is the step size, as we saw, cannot be constant. So if it is constant, then that's a problem, right? So you typically reduce your step size over time, right? So one typical way to reduce this is what people do is they reduce it like this, or some constant by t. right? So as your number of iterations grows, this kind of goes to 0, right? So you can actually show that for certain choices of step size, right? So such that your step size is such that you will be able to go from any point to any point. The step size should not be such that even if you travel infinitely, you won't be within a small ball. So you should be able to go from any point to any point. That is one necessary. Correct. So, but we don't know where the minimum is. So, I mean, what I'm saying is, if you sum up the step size, if I take a step in this direction, keep taking a step in this direction, then I should be eventually be able to travel as much as I want to, right? But at the same time, I should be making smaller and smaller steps as I go along, right? So, and this is one choice of step size that guarantees that. So, basically, you want the sum of this to be like infinity to diverge, but then I think one of the conditions is your sum of the squares of this should actually be constant. So these are technical conditions that you want to put on the step size, for which you can show your gradient descent actually provably converges. So in practice, typically this constant is chosen by different, in different methods. You can try different constants and pick one that works well for you. Typically it is C by T. That is one way to choose step size. Any other questions at this point? Okay. Thank you. I'll stop here for the class. Yeah.